So now we are going, they satisfy anti-commuting rule, gamma 1, gamma 4 plus gamma 4, gamma 1. As I said, for it will work out for all the other gamma matrices too, as I said. So gamma 1, gamma 4, this is for gamma 1, this is for gamma 4, plus this is for gamma 4, this must be your gamma 1. You do the matrix multiplication, you will get the answer as like this. You do the matrix multiplication, you will get the answer as this. You add these two, 0, 0, 0. This will become 0. This also will become 0. 0 plus 0, 0. So answer is 0. So it's very clear that they anti-commute with each other. So gamma matrices themselves will anti-commute with each other. Okay? Any doubt? So that will be the first property is anti-commuting property. Okay? Suppose if it is itself, then that will commute. If it is with others, it will anti-commute. You should not forget. Okay? Gamma 1 with gamma 1 commute. Gamma 1 with gamma 2 anti-commute. Okay? So gamma matrices are Hermitian, alpha matrices are Hermitian, beta matrices are Hermitian. So that's why the Hamiltonian of Dirac equation, that also is Hermitian. So similarly, if alpha and beta are Hermitian, gamma matrix also will be Hermitian, and we can say that the covariance form of Dirac equation also is a Hermitian. Is it okay? Only then we can have a real values, otherwise it is meaningless. So we have gamma matrices are Hermitian and the square is equal to unity. Okay, all gamma matrices squares will be always unity. Just now we have seen gamma 1 squared equals gamma 2 squared equals gamma 3 squared equals gamma 4 squared equal to 1. Now we will go for Hermitian or not. We are going to check. Okay, first before that the square is equal to unity or not, we are going to check. Okay, as I said just now, gamma 4 squared equals 1. So gamma k squared, k stands for 1, 2, 3. We can do it for any other things, 1, 2, 3. So now gamma k, the expression for gamma k is this one. So this multiplied by this, which is equal to minus plus I into I squared. So you have minus sign. So minus beta alpha k, you have beta alpha k. Any doubt? Now I am going to interchange this beta alpha k. When I am going to interchange this will become a minus sign. So this will become minus, that minus and minus will cancel. You have beta alpha k beta. Any doubt? Now put together, you can write this as beta alpha k and beta. Alpha k is nothing but alpha k squared. Remaining term beta squared is nothing but your beta squared. Beta squared alpha k squared, which is nothing but 1 multiplied 1, that will give you 1. So their square is equal to unity. Okay, any doubt? So gamma 1 squared, gamma 2 squared, gamma 3 squared, as well gamma 4 squared, all will be equal to 1. So very simple 1 mark question, as it's very important concept. So or otherwise we can, this is we have done in a different way. Okay, we can done it through the matrices. Okay, we can do it through the matrices. So gamma mu squared equals 1. So just now we got this result, which is nothing but what we call this is self-inverse technique. So this is nothing but a self-inverse technique. And we know that gamma 1 equals minus I beta alpha 1. We know this one. So now we are going to do the same result in terms of matrices. So gamma 1 equals minus I instead of beta, the fourth coordinate. So which is nothing but this. Okay, and your alpha 1 is nothing but in terms of sigma 1. So 0, sigma 1, 0. And matrix multiplication will give you this answer. Okay, so your gamma 1 squared equals 0 minus I sigma 1 0 multiplied by the same thing. So 0 minus I sigma 1 0. Now you are going to multiply this. When you are going to multiply with the matrix multiplication, will give you sigma 1 squared, and that one will give you 0, and this component will be 0, and this will be sigma 1 squared. The answer is, this will be 1 and this will be 1. So answer is 1. So gamma 1 squared equals 1. Okay, any doubt? So now we'll go for the fourth one, gamma 4 squared, for example. So this becomes I0, 0 minus 1. This is your beta multiplied by beta, matrix multiplication. So that will give you I squared 0, 0 I squared. The answer is 1. So either we can prove by this way or by means of matrices. Both the ways, this will work out. Okay, gamma mu squared, which is equal to 1. Okay, Now we will go for the third property. The third property is gamma 4, gamma k, they will anti-commute. As I said just now, gamma k with gamma 1 anti-commute, gamma 4 with gamma 2 anti-commute, gamma 4 with gamma 3 again anti-commute with each other. Okay, so now gamma 4 is nothing but beta, we know already, and your gamma k is nothing but minus I beta alpha k. And what is this one curly bracket? As I said, this will anti-commute. Yeah, this anti-commute. So anti-commute means AB plus BA, okay, which is equal to 0. So now AB is nothing but this one. So you have minus I beta square alpha k minus your BA. So this multiplied by this will give you minus I beta alpha k beta. Any doubt? So your beta square is nothing but 1. So minus I alpha k plus I am going to interchange this one. Beta alpha k as alpha k beta. Here one more beta is there. So beta square is nothing but 1. Okay, so minus I alpha k plus I alpha k is nothing but 0. Okay, so if you are going for gamma 4, let us see. As I said earlier, can you remember? The gamma matrices itself will have commute. With others it will anti-commute. So AB plus BA equals 0. AB plus BA is not equal to 0. Let us see. Okay, so gamma 4 itself anti-commutes are not with gamma 4. We are going to find out. So your gamma 4 plus gamma 4. Simple. AB plus BA. Is it okay? I repeat. See, this is your gamma 4 A. This is your gamma 4 B. Then plus BA. So gamma 4 plus gamma 4. What is gamma 4? It's nothing but your beta. So beta multiplied by beta. So beta square. Beta square plus beta square, answer will be 2 beta square, which is equal to 2. See, as I said, it itself will not anti-commute. Lab is equal to 2. Any doubt? Come on. So now we will go for the fourth one. Gamma mu. So gamma mu is nothing but minus I beta alpha mu. Gamma mu is nothing but minus I beta alpha mu. Now we will go for the same operation. AB plus BA. Okay, same anti-commuting rule. So we will go with the same anti-commuting rule. So we will have AB. Come on, I repeat. Minus plus. Your I into I squared minus 1. So you have minus beta alpha mu. Any doubt? Now we will go for BA. So this term will be first, this term will be second. Again as it is. Minus plus I into I squared minus 1 will give you this term first. So minus beta alpha mu. Any doubt? Now I am going to change this term. Beta alpha mu is nothing but minus alpha mu beta. So I can remove this minus sign, interchange this one. So you have alpha mu beta, this beta is here, alpha mu. Similarly, I can interchange this one with a minus sign. So minus plus will go with plus alpha nu, this beta alpha mu. What is beta? Beta squared is 1. What is here also? Beta squared is 1. You have alpha nu plus alpha mu, which is nothing but your Dirac delta function, which is equal to 2 del mu nu. Suppose if it is not equal, this will become 0. If it is not equal, so this will anti-commute with each other. Suppose if it is equal, so this will become alpha mu. This will become alpha nu. So this will become 2. 1 plus 1. So this will become 2. Is it okay? So this is what another property says. So Dirac matrices are Hermitian, as I said earlier. Dirac matrices are Hermitian. Hence Dirac Hamiltonian is also Hermitian. As I said earlier, alpha and betas are Hermitian. Alpha and betas are connected with the gamma matrices. So gamma matrices are Hermitian. If gamma matrix is Hermitian, surely the Dirac Hamiltonian also is a Hermitian. So now, what is Hermitian? The rule is gamma dagger mu equals gamma mu. A dagger equals A. It's a Hermitian matrix. Okay, A dagger equals A. So gamma mu dagger equals gamma mu. Now we know that gamma mu, expression for gamma mu is nothing but minus I beta alpha k. So just raise it to dagger now. If it is dagger, you have to change it to components into complex conjugate. So this minus I becomes plus I. See, plus I. And that's a rule says that, which you have learnt in quantum mechanics 1, and which says that AB whole dagger is equal to B dagger A dagger. So this becomes alpha K dagger beta dagger. So AB whole dagger equals B dagger A dagger. You have to change and write. That's a rule. Okay, but we know that alpha K dagger equals alpha K. It's a Hermitian matrix, which we learnt in the last unit. Beta dagger also is equal to beta. So we can write alpha K beta. Now I am going to interchange this. When I am going to interchange this, this will become a minus sign. So minus I beta alpha K. What is this one? This is nothing but your gamma mu. We started with gamma mu dagger. So gamma mu dagger equals gamma mu. So simple. It's a Hermitian matrix. So mu stands for 1, 2, 3, 4. For all the other matrices, it will work out. See, gamma 4 equals beta dagger, which is equal to beta, which is nothing but your gamma 4. We have used those conditions in the slide. Any doubt? So all Dirac spinors, Dirac matrices are Hermitian, and thereby the Hamiltonian of Dirac is also a Hermitian. Okay, is Hermitian. Now the last title, which is nothing but traces. As I said, traces are nothing but adding all the diagonal elements in a matrix. Okay, so we are going to add all the diagonals, traces. So the Dirac matrices are traceless matrices. The very good example that we have learned is very simple one, all sigma matrices. We just learn all sigma matrices, no diagonal elements. Okay, now what about beta matrix? Beta equals 1, 0, 0, minus 1. You add, so that will become 0. So immediately we can say this is a traceless matrix. Okay, we will find out. The trace of gamma k, K stands for 1, 2, 3. The trace of 0 minus I sigma k 0. You add the diagonal elements? 0. What about trace of gamma 4? Just now I said trace of 1, 0, 0, minus 1 or I 0, 0, minus A. Answer is 0. Simple. Okay. Then 8th property. The product of, this is very important property which we are going to learn. The product of all gammas is nothing but gamma 5. Okay, which we are going to learn now. Okay, the product of all gammas is nothing but gamma 5. The product of all 4 gamma matrices is often used in the theory, and it is given as a special symbol, what we call this as gamma 5. So you are going to multiply all the 4 gamma matrices. Gamma 1 multiplied by gamma 2, matrix multiplication. Gamma 2, gamma 3, gamma 4 will give you gamma 5. Your gamma 5 is given as 0, minus I, 0. Okay. Now, gamma 5 is also a Hermitian. We are going to prove this one. We know that gamma 1, gamma 2, gamma 3, gamma 4, all gamma matrices are Hermitian. And left hand side is a Hermitian. So right hand side must be a Hermitian, no other way. So we are going to prove that gamma 5 is also a Hermitian. So now gamma 5 dagger. So this is gamma 5 is nothing but gamma 1, gamma 2, gamma 3, gamma 4. So gamma 1, gamma 2, gamma 3, gamma 4. So each can be represented in terms of, as I said just now, the rule, we have to interchange and write. Can you remember? Whole dagger will be gamma 4 dagger, first one. Gamma 3 dagger, gamma 2 dagger, gamma 1 dagger. What is gamma 4 dagger? Gamma 4. What is gamma 3 dagger? Gamma 3. So gamma 3, gamma 2, gamma 1. Okay, now I am going to bring this term front side, gamma 1 to front side. If I take gamma 1 to this side, one minus exists. Very, very important one. So I am going to bring this gamma 1 to this side. So this will become gamma 1, gamma 2 with a minus sign. That gamma 1 I am going to bring this side. So this will become plus, plus, minus, minus, plus. I am going to bring this gamma 1 here inside, that is in front. So that will become minus. See, minus gamma 1, gamma 4, gamma 3, gamma 2. Already I brought gamma 1 front. Is it okay? Any doubt? Now I am going to bring gamma 2 front. So gamma 2 front means that will be one minus sign. Again this will, I am going to bring this here. So this is plus. So you have minus gamma 1, gamma 2, gamma 4, gamma 3. Is it okay? No. See, I am going to bring gamma 1 front side. Okay, gamma 1, I am going to take this gamma 1 front side. So I am going to bring this gamma 1 front side, means this will become minus gamma 1 gamma 2. Again one more this one step here, then this will become minus minus plus. Again one more step, that will give you minus. So minus gamma 1, gamma 4, gamma 3, gamma 2. I am going to bring this gamma 2 front, okay, at the back side of gamma 1, front side of gamma 4. So this will become minus minus plus, plus with another minus, only one minus is there, another minus is, so plus multiplied by minus, that will be minus. So gamma 1, gamma 2, I have brought already gamma 2, so gamma 4, gamma 3. Any doubt? I am going to bring this gamma 3 front side, so that will come with a minus sign. So minus minus plus, so gamma 1, gamma 2, gamma 3, gamma 4. What is gamma 1, gamma 2, gamma 3, gamma 4? Gamma 5. We started with gamma 5 dagger. We ended with gamma 5. So it's a Hermitian matrix. Very simple idea. So we are going to bring gamma 1 to the front side. This will have one minus sign. Don't forget. Okay, one step minus sign. Another step plus. Another step minus sign. It goes on. Any doubt? So clearly says that the product of all gamma matrices is a Hermitian. Because each gamma matrix is Hermitian, the product also is a Hermitian. Simple idea. Okay. Now gamma anti-commutes with all gamma mu's. We have already seen this one. However, just to recall, okay, gamma phi, we have already seen this property. Can you remember? Gamma 1, gamma 2, gamma 1, gamma 3, gamma 4, all will anti-commute with each other. Now we have introduced gamma phi. We have introduced gamma phi. Whether this will anti-commute or not. So gamma phi with gamma mu plus gamma mu gamma phi is also equal to 0. So this will also anti-commute. So now we are going to prove this one. Okay, let us see. So gamma phi, gamma 1 plus gamma 1, gamma phi equal to 0. This is applicable for all the gamma matrices too. For example, gamma phi, gamma 2 plus gamma 2, gamma phi. That also will be equal to 0. Gamma phi, gamma 2, gamma 3, gamma 4, gamma phi with gamma 4. That also will be equal to 0. So that will have anti-commute. First we will prove this one. So we have gamma phi, gamma 1. What is gamma phi? Gamma 1, gamma 2, gamma 3, gamma 4. This gamma 1 is here. As usual, I am going to bring this gamma 1 front. So this will have minus sign, and again this will have plus sign. Again one more, so minus sign. So minus gamma 1, gamma 2, gamma 3, gamma 4. Any doubt? So what is this one? Gamma 1, 2, 3, 4, which is nothing but gamma 5. So this is minus gamma 1, 5. So gamma, we started with the gamma 5, gamma 1. You bring this term to this side. So this is equal to 0. Is it okay? So your assignment, as I said just now, this will work out for all the other gamma matrices too. You just have this assignment. Gamma 5, gamma 2 plus gamma 2, gamma 5 is also equal to 0. Similarly, you can go for gamma 5, gamma 3. Similarly, you can go for gamma 5, gamma 4 plus gamma 4, gamma 5, which is also equal to 0. So now we will go for this property. Gamma 5 squared equals identity matrix. So we know already gamma 1 squared equal to 1, gamma 2 squared equal to 1, gamma 3 squared also is equal to 1, gamma 4 squared is also equal to 1. We know already. Now we have introduced gamma 5. So that's why we are going to check whether gamma 5 squared is identity matrix or not. We are going to check. And we know that gamma phi, expression for gamma phi is this one. So this is for your gamma phi. Simple. Gamma phi is nothing but gamma 1, gamma 2, gamma 3, gamma 4. I am going to bring this gamma 1 front side. As usual, the same technique. Bringing gamma 1 to this side. So that will give me minus sign. Bring this one term here. That will give you plus. Again bring this term. That will give you minus. So you have minus. Gamma 1, gamma 1, gamma 1 square. Answer is 1. So you have gamma 2, gamma 3, gamma 4. Already we have got this one. So gamma 2, gamma 3, gamma 4. Any doubt? Now we are going to bring this gamma 2 front as usual. So you have gamma 2 front side. This will become minus. Again we are going to bring one more term. So that will give you plus. So minus Gamma 2, gamma 2, gamma 2 square, answer is 1. So we have gamma 3, gamma 4, gamma 3, gamma 4. Now I am going to interchange this with a minus sign. So this will become a minus sign. So you have minus minus plus, you have gamma 4, gamma 4, gamma 4, gamma 4. That's all. You can also do it like this. See, I'm going to bring this gamma 4 here, okay, then gamma 4 here, gamma 4 here. Doesn't matter. Anything. Or else just take gamma 3. You just take gamma 3, you bring it to this side, so that will be gamma 3, gamma 3, gamma 4, gamma 4. So gamma 3 will give you 1. Gamma 4 will give you 1. Correct? So we can write this as identity matrix. So gamma 4, which is nothing but your identity matrix. So we can prove that gamma pi squared is also an identity matrix. So we have proved. Since the trace is a sum of eigenvalues, so we know that sum of in a matrix, sum of eigenvalues which must be plus or minus 1. The number of positive and negative eigenvalues must be equal. So this is the conclusion. So this means that the dimension of n of the Dirac matrices must be even. So that's why I said this will become 2 by 2, and after that 4 by 4. It will be always in the even number. So they can only have 2 by 2 matrix or 4 by 4 matrix and goes on. So they must have an equal number of plus 1 and minus 1 eigenvalues. So they must be even dimension, which is nothing but 2. Okay. So in this class, we have introduced the covariance form of Dirac equation, and we have studied some properties of gamma matrices, which is nothing but your alpha and beta. Then traces of gamma matrices. So these questions are very important, and this is as I said, this is the continuation of the previous relativistic equation, relativistic quantum mechanics. Okay, thank you students. We will see in the next class.